Thank you. I would like to thank the organizers for giving me the opportunity to talk here and for organizing this wonderful conference. Yeah, I'm going to talk about differential Galois theory of a large field of constants. And this is joint work with David Harbater, Julia Hartmann, and Florian Popp. And we are solving the inverse problem over a certain class of fields. And the field of constants of these fields are not necessarily algebraically closed. And so I would like to start by recalling how the differential Galois theory works in this case. Okay, so we have all fields in my talk are of characteristic 0. So we have a field F with a derivation delta, characteristic 0, and field of constants is called K. So and then if you have a linear differential equation over F, you would like to have a solution ring, so a PV ring, Picard-Vessier ring. And what you need to do is you need to find a fundamental set of fundamental solution matrix in some differential field extension and adjoin all entries and the inverse of the determinant. But you need to make sure that you don't get new constants in this ring and also that it's a differential simple ring. All right, and if the constants are algebraically closed, you can always have such a PV ring by just modding out a maximal differential ideal out of the polynomial ring. If the constants are not algebraically closed, it might happen that it doesn't exist. But if you are over a rational function field with derivation differentiation with respect to x, then it always exists because you just take inside, you can go inside the Laurent series. You take some element A. Oh yeah, sure. Sorry. So you just take an element A and K where you don't have any pole in your matrix, and then you can go can find the solution matrix inside the Laurent series in X minus A. Okay. Okay. So in my talk, I will only talk about rational function fields, and so we do know that PV rings exist. They might not be unique. In fact, Michael mentioned in his talk yesterday that they are classified by H1 in a certain sense. Okay, so now for the differential Galois group. If the constants are algebraically closed, this is the definition of the differential Galois group. You take the automorphisms of your solution ring that communicate with the derivation. If K is not algebraically closed, this is the definition for the K rational points. So this is the linear algebraic group over the constants. And then to know what the L rational points are for an extension L of K, you just tensor R over K with L and F over K with L. And so you define this functorially. Okay, but in any case, it's a linear algebraic group over K. So, and we are interested in the inverse problem. So the question, which linear algebraic groups are differential Galois groups over your given field? So in other words, given the group G, can you find a PV ring for some differential equation such that the differential Galois group of this PV ring is the given group? Okay, so there are some classical results here. If you are over C of x, then every linear algebraic group over C is a differential Galois group. And that's the result by Tretkov and Tretkov from 1979. More generally, if you are over K of x and K is algebraically closed, then the same is true. And, excuse me? Yeah, everything is K characteristic 0 in my talk. Kovacic worked on the case of the solvable groups, and then in the 90s, Michi and Singer proved this for connected groups, and finally the last step was proved by Julia Hartman in 2002 to go from connected to non-connected groups. By the way, the same is true for the real numbers R. That's a result by Tobias Dückerhoff. And another classical result, not of a rational function field, but in the local case, let's assume maybe for simplicity that K is algebraically closed, and we are working on the Laurent-Sears field, differentiating with respect to X. Then not that many groups occur. In fact, only certain abelian groups. So the quotient, the finite quotient is cyclic, and the connected component is either torus or torus cross GA. Okay. Another case. So if you are over a rational function field over the Laurent series field, so these are the constants. Then we showed, using the method of patching, that every group occurs. So this method of patching allows you to glue PV rings together under certain conditions, assumptions, and the PV ring you obtain has differential Galois group that is generated by the groups of the smaller PV rings you glue together. And so in this way you can construct PV rings with big differential Galois groups. And this method of patching was introduced by David Harbert and Julia Hartman, and it works over fields, over function fields, over complete discretely valued field. So this is a complete discretely valued field. But really, what we're really interested in is K of x for any K, right? So we would like to go from here to K of x. Okay, so maybe one other field that's interesting. So if you look at a fraction field of the power series in two variables, T is constant, and then as a corollary of this, we can show that also every group occurs. And I think that's a bit surprising, because here only very few groups occur, and somehow if you mix in a constant, then every group occurs. Yeah, but maybe it's not that surprising, because it was known that the same phenomenon is true for finite groups. Okay, so every linear algebraic group occurs. That's a corollary of this one. Okay, so now what I would like to talk about today is if we are over a large field, and I will explain what a large field is. A large field of infinite transcendence degree then also every group occurs. And that's a new result. And we don't use the method of patching, but we extract this from this result. So this field, K of T, is also large enough infinite transcendence degree of Q. So in a way, this is a generalization of this result. But actually, we use this result to prove the new result. So we somehow descend from this field to K. Okay, so large fields were introduced by Florian Popp in the 90s when he observed that in the classical Galois theory over function fields, a lot of results were known, and he observed that the constant fields of these function fields where the inverse problem was solved all share a common property. And then he conversely proved that this property is enough to solve the inverse problem. And then later, so let me first say what the property is. So a field is large if for every smooth curve the following holds. If you have one k rational point, then you have infinitely many. Okay, and so then later, a lot of fields were proven to be large, and in this way, we also got back results in classical Galois theory. Okay, and maybe one criterion for large, there are a lot of criteria, but maybe just one. So this is equivalent to K being existentially closed inside the Laurent series field. Okay, some examples of large fields. Okay, so every algebraically closed field is large. Also, every pseudo-algebraically closed field is large. Every field that is complete with respect to a discrete valuation. For example, the reals QP, and since QP is of infinite transcendence degree, our result in particular holds over QP of X. And Laurent series fields, and more generally, fields that are fraction fields of Henselian domains are large. And okay, examples of non-large fields, of course, Q number fields, rational function fields. These fields are not large, but a lot of other fields are large, or maybe are conjectured to be large. For example, the maximal abelian extension of Q. It's an open problem whether that's a large field or not. Okay. So maybe just one proposition that's not differential algebra, but just on large fields. So if you have a large field K, infinite transcendence degree, and you have a subfield of the Laurent series field, right? So I said before that somehow we want to descend from Laurent series to K. So we start with such a field K1 that's finitely generated over Q. Then you can embed this field into K. And obviously this assumption is necessary for this proposition. So, and the proof, what we do is we write this field K1. This is the function field of a smooth integral variety over this field. And the function field embeds into this Laurent series field, which means the generic point lies in here. So you have a K of t rational point. And since the field is large, K is existentially closed in here, so you also have a K rational point. So now we have a variety over this field with a K rational point. Then we show by induction on the dimension of this variety that we can embed in here. And so the basic idea is we may assume that it's affine because the rational point lies in some affine part, and then so it's of the form spec of R, and then we pass from R to some localization of R to make the dimension smaller, and that's the idea of the induction step. And in that way, we can prove that we have such an embedding. Yeah. And now the result actually also holds for more general fields, so you don't necessarily need to assume that's a rational function field. You can also go up to finitely generated extensions. So you have a large field, infinite transcendence degree, and you have a differential field F, finitely generated over K, with field of constants K. Then, as I said before, every linear algebraic group is a differential Galois group. Over F. Okay, so first thing we can do is we may assume that it is the rational function field. So that's a trick that we call the Kovacic trick, because Kovacic, I think, was the first who used this trick in case K is algebraically closed and G is a connected group. Then he showed that if you can show that every power of G occurs over K of X, then also G occurs over every finitely generated extension. And we generalize this trick in this other paper. So we generalized it to arbitrary constant fields and also to non-connected groups. Okay, and now this it's not on the board anymore, but this result we obtained over the Laurent-Series field using patching now says that there exists a PV ring over this bigger field over the Laurent-Series field with group G. But what we really want is a PV ring over K of X with group G. So now we descend to K of X. Okay, so now we somehow need to descend to finally generated extensions of Q. So let's first descend our group, or choose a field K naught finally generated such that G is defined over K naught. So G is a group defined over K, has defined by finitely many equations, so you just adjoin all coefficients and get the group G naught over K naught such that G is the base change of G naught. Okay, that's easy. Next, we fix a finitely generated extension K1 of this field K naught such that the whole PV ring descends to K1 of X. And we may choose this, of course, inside the Laurent-Series field, because that's where the PV ring comes from. Okay, what does it mean? This means there exists a PV ring R1 over K1 of X with group G, or more precisely with group G naught base change to K1. Okay. So how do we do this? So this is a PV ring. So it comes with the differential equation. The differential equation has entries in here, finitely many. So we join all coefficients of all entries. And then we also join finitely many things such that the fundamental solution matrix can be written over this field with relations over this field. And also the fact that the ring is generated by the entries of the fundamental solution matrix and the inverse can also be written by infinitely many equations with finitely many coefficients. So we adjoin all of these, and we obtain this field K1. Now we can use our proposition. We have a finitely generated field K1 that's contained in the Laurent-Series field. So we know that we can embed this field into K. Okay. And now it's easy because now we can just base change this ring R1 from K1 of X up to K of X. If K1 is contained in K, then we can just base change back up. So now this ring, going from K1 of X to K of X, is now a PV ring over K of X with group So this says group G not K1. So we have go from G not from K not to K1, go back from K1 to K, and since this is an embedding over this intersection, this is just our group G we started with. So that's the PV ring we wanted to construct. It has group G. Okay. We can also do a bit more. So we can also solve split differential embedding problems, which is a bit stronger, which means that you can not only construct a PV ring with a given group, but you can also do it in a way that it fits together in towers with the quotients. And the proof is very similar. You just have to descend the given data, and then you use this embedding. In the proof, we also use a joint result with Michael Wiedmer on embedding problems that we used before for the complex numbers, but the rest is very similar. Okay. Maybe one more remark. Of course, we are interested in getting rid of the condition of infinite transcendence degree. We believe it's true. We are working on it, but the proof is going to be different, right? I mean, this is a very simple proof, just using this proposition, this criterion on large fields. If the transcendence degree is finite, we will have to work with more technical construction. So we are working with specialization, so in a similar flavor of in the talk of Ruyong Feng. So we will somehow have to specialize from here. So this is embedding. Here we are embedding the field into K. In the other project, we need to specialize, and we need to know that there's a good specialization. If we specialize these elements in K1, so we map from K1 to K, or from an algebra to K, we need to know that there are some good specializations, and the main problem is that if you specialize, that there are no new constants in the PV ring that you specialize to. Okay, so thank you for your attention. Okay, so the question is, can we use this tool to obtain realizations over small fields? What do you mean by small fields? Okay. No, I mean with this proof, no, because we really use this proposition. With the other technique, with the specializations, maybe certain small fields. I mean, surely not every, because Q would be very interesting, but this is not in our reach, I think.